Welcome to the presentation of our CVPR 2026 paper titled MatchED, Crisp Edge Detection Using End-to-End Matching-Based Supervision. In this work, we focus on a long-standing challenge in edge detection, producing crisp, 1-pixel-wide edge maps. While modern edge detectors are highly effective at identifying edges, their raw outputs are often thick or blurry, which limits precise boundary localization. Existing solutions generally follow two main directions. The first is to detect edges and then apply handcrafted post-processing, such as NMS and thinning. However, these steps are non-differentiable and prevent fully end-to-end optimization. The second direction is to design specialized losses or architectures for crisp edge detection, but these methods are still far from optimal and often continue to rely on post-processing. Our solution is MatchED, a plug-and-play learnable module that can be attached to an existing edge detector. It is lightweight, adding only about 21,000 parameters, and its purpose is to learn crisp edges during training instead of relying on post-processing at test time. Here we show the overall MatchED pipeline. First, the base edge detector F takes the RGB image I, and produces a raw edge map ER. Then, we append MatchED to this output. MatchED takes ER as input and generates the crisp edge prediction EC. In this way, MatchED can be integrated into existing edge detectors as an additional trainable module. The key idea is to align the crisp prediction with the ground truth. For each predicted edge pixel PC and ground truth pixel PG, we define a matching cost using spatial distance and prediction confidence. This cost is computed only when these three conditions are satisfied. In this way, MatchED encourages confident predicted edges to align with nearby ground truth edges. After defining the cost matrix, we solve an optimal 1-to-1 bipartite matching problem. This is important because each predicted edge response should be assigned to at most one ground truth edge pixel. By enforcing this 1-to-1 correspondence, we discourage multiple neighboring pixels from being activated for the same ground truth edge, which helps prevent thick edge predictions. After obtaining this optimal assignment, we construct the matching-based ground truth label. Finally, if any original ground truth edge pixel remains unmatched, we restore it in the matching-based ground truth so that missing edge regions can still be learned in later iterations. The optimal matching gives us a new matching-based ground truth label. MatchED is then trained with binary cross-entropy between its crisp prediction and this matching-based label. The final objective combines the matched loss with the original loss of the base edge detector. For evaluation, we use these metrics. We report these metrics under two different protocols, standard evaluation and crispness-emphasized evaluation. We evaluate MatchED on four popular datasets: BSDS, NYU, MultiQ, and BiPED. Our experiments cover comparisons with crisp edge detectors, comparisons with state-of-the-art methods under both CEval and SEval, and visual results showing the effect of MatchED. First, we compare with existing crisp edge detectors using average crispness. MatchED clearly improves crispness across different datasets. For example, on BSDS, PyDNet plus MatchED reaches 93% AC, compared with 47.6% for diffusion edge. Similar large gains appear on MultiQ and BiPED. Under CEval, where raw outputs are evaluated without post-processing, MatchED gives large improvements across different base models. On BSDS, PyDNet improves from 57.8 to 80.0% ODS, ranked from 63.1 to 81.9%, diffusion edge from 74.9 to 83.3%, and SODG reaches 85.4% ODS. On NYUD, similar to BSDS results, MatchED consistently provides substantial gains across all three metrics, across different base models. Under standard evaluation, where NMS and thinning are applied to only base model results, MatchED remains competitive with their results. This is important because it shows that the raw matched outputs are already close to what handcrafted post-processing is trying to produce. The visual results clearly demonstrate the effect of MatchED. The green rectangles highlight the improved cases in the zoomed-in views. Compared with the base diffusion edge output, which is a state-of-the-art crisp edge detection method, MatchED produces thinner and better localized edge structures. In conclusion, MatchED addresses the long-standing crispness challenge in edge detection through end-to-end, matching-based supervision. It is lightweight, plug-and-play, and can be integrated with diverse architectures. Our results show that MatchED achieves the best performance among existing crisp edge detection methods. More importantly, it often matches or even surpasses standard post-processing, while producing crisp edges in a fully trainable manner. One limitation of MatchED is that hyperparameter tuning requires retraining. As future work, we plan to extend this matching-based supervision idea to other computer vision problems where handcrafted post-processing is commonly used. For more details, visit our web page. Thank you for listening.